Choosing an engineering college can be an extremely difficult task. After all, Karnataka itself has over 200 of them. Picking the right one can greatly enhance your learning, life experience, and even job opportunities after the course. In the next few minutes, you will see how and why Don Bosco Institute of Technology is the college that is designed to make you a successful engineer. Founded in the year 2001, Don Bosco has been providing quality education for 15 years now and currently offers 7 undergraduate courses, 8 postgraduate courses, and 3 research centers for pursuing doctoral programs. The Bachelor of Engineering course is as much about learning via hands-on experiments as it is about theory. Don Bosco focuses on providing students the best of laboratory facilities to complement the able faculty and the university curriculum. In fact, given the superior status of our infrastructure, the university and the regulatory body, AICTE, has approved an impressive 740 seats for the engineering program. This high number itself is a testament of the number and quality of equipment available to our students.
I see the startup world or industrial research labs in India are product innovations, incremental innovations, or business model innovations. Keeping in mind, we are planning to make Don Bosco Institute of Technology not only a quality institute, but also virtual university in coming years.
Across different specializations, the college employs experienced faculty who undergo regular faculty development courses so that students always get the best of teaching. For instance, the Computer Science and Engineering Department has 40 faculty members, and some of them are pursuing research alongside teaching. The results of such a focus on experienced and skilled faculty is telling. Currently, 80% of all students who enter the engineering courses complete the course successfully. The figure is higher than the average. In 2013, the university's 6th rank in Information Science and Engineering was bagged by Don Bosco student. While technical education is most critical in an engineering course, Don Bosco recognizes the need for creating an atmosphere where all-round personality and life skills development can happen alongside the technical course. The college spans an impressive 36 acres and gives students opportunities to pursue a variety of sports like softball, kabaddi, badminton, wrestling, judo, and athletics. Don Bosco students have won several awards in recent years in all of these sports at university level. There's also yoga to help students relax both mentally and physically. At Don Bosco, several cultural events are held throughout the year. The annual Intercollegiate Fest of Don Bosco, being held on a large scale with much pomp, is popular and sought after engineering colleges in Bangalore. This year, the event saw celebrity performances and a DJ night for the students. Apart from this event, there are regular inter-college cultural and technical events held throughout the year.
The ignited mind of the youth is the most powerful resource of this planet. To become a center of excellence, to build an innovative research environment, to match the growing needs of society and industry by creating relevant infrastructure, quality human resource that is essential to empower future professionals.
You don't have to just take our word for the excellence in teaching and facilities. Take one look at the corporates who associate with us or offer jobs to students straight out of Don Bosco, and you'll know that the college is respected in corporate circles. Intel, Microsoft, Oracle, Siemens, and Bosch are some of the companies that associate with Don Bosco to run academic programs and offer jobs to our students. Other recruiters include the who's who of the technology world: Infosys, Tech Mahindra, Accenture, Cognizant, Samsung, and Cisco. Just few names amongst many. Hostel facilities are provided for students who come from outside Bangalore. The hostel is much more than a lodging facility. It is a full-fledged living arrangement designed to make students feel comfortable, with all basic needs taken care of, from in-house healthcare to a cafeteria with a variety of foods, from uninterrupted internet connectivity to reading rooms and TV rooms. The hostel has it all. Some students say the hostel is more comfortable than their homes.
The hostel of Don Bosco Institute of Technology is not just a place to stay, but also a place to relax, almost like home.
I love Don Bosco Institute of Technology because education is uncompromised here, but there is still lots of scope for sports and fun activities.
I'm very impressed by the extensive laboratories present in Don Bosco. It makes learning simpler and more effective.
I think a good friend circle is very important in a college, and Don Bosco seems to have attracted some brilliant students, and therefore I have been able to make superb friends here.
Innovations happens when people of different backgrounds think together, challenge each other, and help each other take innovations out.
Life is precious because it is a gift from God. Thank you, Lord, for another amazing day full of so many blessings. A river cuts through rocks not because of its power, because of its persistence. A very good morning to everyone. Thank you to each and every one of you for being with us today. Myself, Krishnaveni, Assistant Professor, Department of Chemistry, Don Bosco Institute of Technology. I take the privilege to warmly welcome all our delegates on virtual faculty development program on recent trends in green chemistry 2021. I would like to formally welcome our respected President, Sir Bailappa, Vayanamak Education Trust, Bangalore, Honorable Executive Director, Sri B. Manjunath Sir, Honorable Secretary, Sri Raghav Bailappa Sir, Dr. T. Hemadri Naidu, Principal, DBIT, Dr. Natraj K.R., Dean and Director, R&D, guest speaker, senior researchers, academicians, and participants, and my dear colleagues. It's a great honor for me to welcome you all once again for one-day faculty development program on 1 week faculty development program on recent trends in green chemistry 2021, being organized by Department of Chemistry, Don Bosco Institute of Technology. Now I request Professor Sushma ma'am to share about our department.
Good morning to one and all present here. I'm Professor Shishma. I'm hereby to speak about the department. The Department of Chemistry has distinguished itself as a center for innovative and pioneering teaching and research in different fields of science. It was elevated to the status of VTU Research Center in 2011 in recognition of its achievements in various fields and receipts for sponsored projects. The major research efforts are focused on areas such as catalysis, reaction kinetics, corrosion, polymers, material science, and electrochemistry. To ignite the quest for chemistry and its versatile application in the young minds of future engineers, the department organizes various activities such as guest lectures, quiz, workshops, conferences and seminars in association with Science Forum Student Chapter. The faculty members in the department are highly active in teaching as well as in research and publish more than 80 research papers in peer-reviewed national and international journals, including two patents. Chemistry Research Center has completed 3 major projects from VTU, KSST, VGST, and one project is ongoing under the supervision of Dr. J.P. Shubha, Department of Chemistry. Department have MOU with few industries to bridge the gap between the academic deliveries and industry needs and thereby improve employability skills of the students. The department has established a biodiesel production unit in 2018 for generating the biodiesel. Also, we have initiated the development of Simaroba path for the utilization of oil yielding trees. Thank you very much.
Thank you, ma'am. Now I would like to request HOD, Department of Chemistry, Dr. A.S. Manjunath sir, to share theme of the FD.
Thank you, ma'am. Very good morning, all. With respect to President Shri B. Bailappa sir, Vayamak Education Trust, with respect to Executive Director, Don Bosco Institute of Technology, B. Manjunath sir, with respect to Secretary Shri Raghav sir, and Principal Dr. A. Madhuri Naidu sir. It is my pleasure to inform about the theme of the FDP. The major theme of this FDP is green chemistry. Green chemistry is mainly concerned the process for producing chemicals commercially as well as the redesign of existing materials so that their disposable at the end of their lifetime will not adversely affect the environment. In terms of chemical process, green chemical methods will preferably utilize recyclable solvents, reusable reagents or catalysts, and starting materials derived from renewable resources. In terms of the material design, the degradation pathways for a particular material are analyzed and then modified to reduce or eliminate the environmental load imposed by the decomposition products. This FDP program will comprise lectures by our invited speakers from various reputed national and international organizations. This FDP aims to help research scholars, academicians, and industrialists to modernize with the materials and green chemistry. The highlights of the topic includes green catalysts and green technology, green chemistry, green nanotechnology, future trends in green chemistry in environment, green synthesis, and sustainable chemistry, and many more. I hope this virtual FDP will gain knowledge among all the participants about the green and sustainable chemistry. Thank you. Thank you all.
Thank you, sir. Now I request our principal, DBIT, Dr. Hemadri Naidu sir, who is backbone for us to share few words and motivate us.
Yeah. Very good morning, all of you.
Good morning, sir.
Am I audible?
Yes, sir.
Okay. Can I continue?
Yes, sir. Please, sir.
Okay. Thank you. Warm and happy greetings to all. Respected Chairman, Executive Director and Secretary of Don Bosco Institute of Technology. I'm immensely happy that Department of Chemistry is organizing 5 days online FDP on recent trends in green chemistry and is going to present a collection of information about recent developments in science in the area of energy, environment, catalysis, and material science. Under the able guidance of our management, this FDP continues to march on the way of success with confidence. The sharp, clear-sighted vision and precise decision-making powers of our management has benefited our college to stay competitive. The dedicated HODs and staff members and disciplined students of DBIT are the added features of our college. For efforts in organizing and participating in this FDP. I wish the FDP all success. And I thank everyone for your patience, attention. Thank you all for giving me the opportunity to share of my views on this wonderful morning. Thank you.
Thank you so much, sir. I also welcome Natraj sir, Dr. Natraj sir, Dean R&D, for supporting us and guiding us. Thank you so much, sir. The power that we have, the knowledge and the influence that we have are beautiful gifts from God to be utilized to serve each other unconditionally. Now I would like to introduce our guest speaker and keynote speaker, Dr. Syed Farooq Adil. Dr. Syed Farooq Adil sir is an associate professor, Department of Chemistry, King Saud University, working in the field of material science, nanomaterial synthesis for energy and catalytic application. He is an assistant editor, journal for Saud Chemical Society. He was a visiting associate, California Institute of Technology, USA, worked in the field of fuel cell material studies. His research interests are nanomaterials for energy, innovations in the synthesis of various nanomaterials, including 2D materials, metal nanoparticles, metal oxide, and mixed metal oxide nanoparticles for energy-related applications. Employment of green synthesis techniques for nanomaterial for prevention of environmental preservation. Graphene and graphene nanocomposites based 2D materials for energy-related applications and heterogeneous catalysis. Application of metal oxide and mixed metal oxide nanoparticle for the sustainable energy process, energy storage application for nanomaterial, and biological application of nanomaterial. And his other interests are catalytic applications of nanomaterial and nanocomposites, environmental remediation application of nanomaterials, and biological applications of nanomaterial. Sir has completed his PhD in chemistry in the year of 2008, Jawaharlal Nehru Technological University, Hyderabad. Sir is authored for 2 books and he has published 2 book chapters in elsewhere publications. He has patent for methods of preparation of metal oxide nanoparticle, method for coating substrate with silver nanoparticles, transesterification of used edible oil for the production of biodiesel. He is having international collaborations with Jonas Gutenberg University, Germany, and Bio-Nano Plasmo Laboratory, Spain, Jamina University, New Delhi, Aligarh University, Uttar Pradesh, India, and Acharya Nagarjuna University, Guntur, India, and Don Bosco Institute of Technology, Bangalore. Huayin Institute of Technology, China, and Quest International University, Malaysia. He has handled many projects. With this short introduction, I welcome you, sir, once again, and I request you to deliver the keynote speech, sir.
Thank you. Thank you for the brief introduction. Are you able to listen to me?
Yes, sir. Yes, sir. Yes, sir.
Audible? So, thank you for the brief introduction. I would like to thank Mr. Bailappa, the president, Mr. Natraj, the principal. Excuse me, just give me 1 minute. Mr. Dr. Natraj, the dean and director of R&D, and Dr. Hemadri Naidu, the principal, and Dr. Manjunatha, the HOD, for this opportunity they have given me. I have to share my slide, right?
Yes, sir.
I'm the presenter now?
Yes, sir. Yes, sir.
See the slides?
Yes, sir.
Okay.
Make it full screen. Sir, make it full screen.
Yes. Is this fine?
Sir.
Yeah, is this fine now?
Sir.
Are you able to see it?
Yes, sir. But it is showing.
Next slide also. Sir, the next slide also is
visible, sir. 2 slides are visible, sir.
Okay, 1 second. Okay. I got it. Is this clear now?
Yes, sir.
Okay. So let's begin. My topic is based mostly about the green synthesis applications for the synthesis of nanoparticles, and I will show how I have used these green synthetic protocols in my laboratory for various applications. So to begin with, nanotechnology was not unknown to man, because it was even used in ancient periods. There were many examples where tinted glasses were mixed with gold, and you could see that the ancient people could see different colors of using them. And this was because the gold was converted to nano size when it was extensively heated while making the glass. However, as the microscopic techniques have evolved, people were able to see the arrangement of atoms, how they look under the microscope. And that is what led to the initiation of this amazing field called nanotechnology. So Nanomaterials, as most of you must be aware of, they are one-dimensional particles with a particle range from 1 to 100 nanometers. Microscopy has helped us to understand that they exist in various shapes and forms, including thin films, nanorods, nanowires. This science of nanotechnology, it deals with the fabrication of the nanomaterial. And why is this fabrication a very important aspect? Because it has been found that these nanomaterials, based on their sizes and shapes, have varying applications. The bulk gold is not reactive. However, gold in nano size is highly reactive, and it has been used for various applications such as catalysis and medicine and imaging. So fabrication is a very important aspect of nanotechnology. And how is that done? So there are various methods how you can fabricate nanomaterials or nanoparticles. However, basically they are classified into two basic classifications. One is the chemical methods, and the other one is the physical methods. Now, physical methods, you deal with arc charge, flame pyrolysis, ball milling, laser ablation. While the chemical methods is you use any chemical reagents or reactants that will help the reduction of metal salts, and you will try to control the particle size. However, these methods have their own advantages and disadvantages. So the chemical methods, with the help of chemical methods, there are three things that are very much possible. One is you can control the size and shape. The desired size and shape can be obtained using a chemical method. And the second very important thing is it can be used for bulk synthesis. And the last is the low cost. So these three are very important parameters if somebody is trying to go for an industrial application. Whereas if you go to physical methods, the advantages are you get a very high quality product. And the most important thing is there is no chemical toxicity. And you are not going to use any chemicals other than the metal salts itself. And here also you can to some extent control the shape. However, both these methods have their own disadvantages. For the physical methods, first of all, as I just told, you use an electric arc, a laser ablation, ball mill. All these require expensive equipment, which is not possible for most of the laboratories. The other thing is, since you are not able to control the reaction chemically, the yield is very low. And the other thing is, you will use high temperature and pressure. Most of the processes use high temperature and pressure, which requires a very high energy consumption. However, the disadvantages of the chemical methods are the hazardous chemicals are used as reagents for reducing the nanoparticles. So now these hazardous reagents, they are a threat to the environment. Moreover, if you use a hazardous chemical for the preparation of nanoparticles, then the possibility of this nanoparticle being used for a biological application is slightly less, because you will not be allowed to go for large-scale residual of the hazardous chemicals can come along, and the biological applications will be more toxic rather than helpful. The other thing is the chemical methods. You may control the size and you may control the shape. However, they need stabilizers so that the size and shape is sustained without agglomeration. So now, what is the thing that we are looking for actually? See, the requirement is we need high yield, because anything that needs to go for an industrial scale of production, you need to have high yields, because otherwise you'll go in huge loss. Then ambient conditions are very much necessary, so that the power consumption and other things will come down, which will help you have a less expensive product. And we have to try to see to it that whatever we design, whatever we do, it should be environmentally feasible. Hence, the concept of combination of wet chemistry and green chemistry was introduced. Now, what is green chemistry? The green chemistry is development and implementation of methods wherein one can eliminate the use of hazardous substances or generation of hazardous substances as a byproduct. So this is a very, very important concept that we will see in the future, in the further slides. So how can we achieve green synthetic protocols? Green synthetic protocols are by use of proper solvents, reductants, and stabilizers. Solvents, there were times where ionic liquids were used as solvents. Ionic liquids were used as solvents because they had no vapor pressure and they would not vaporize and pollute the environment. However, that has been reduced. The use of ionic liquid has been reduced because the process of extracting the product from ionic liquid was again would require hazardous solvents. So you have to be very careful as to what you are using as solvent, what you are using as a reducing agent, and what one has to use as a stabilizer, so that the nanomaterials that you obtain should not lose their properties. So the commonly applied methods for this is the citrate reduction, where sodium citrate is used for reducing of metal salts. The other solventless method is the electrochemical reduction, where electrochemically you can reduce the metal salts. Microwave reduction, sonochemical reduction are also possible for the synthesis of nanoparticles. There are some studies where supercritical liquids and ionic liquids also have been used for this. However, the growing demand of multifunctional reactants is where one intends to see that the reactant plays two roles. It should reduce the metal salt as well as stabilize the nanoparticles that are obtained. So in this aspect, biogenic materials such as marine organisms, microorganisms, and plant extracts have been selected. Since I have been working on plant extracts, I would like to give some information about them. Plant extracts are nothing but crude mixtures of extracts from different parts of the plant. These extracts have been found to contain a rich library of natural chemical compounds, which are known as natural products. However, apart from the use in nanotechnology, these natural products were also used as Ayurvedic and Unani medicines for a long time, and these natural products have been the key players in identification of active compounds for various diseases such as anti-cancer and antibiotics. So why plant extracts? Why should one go for plant extracts? Plant extracts are very easily available, and you don't have to spend money to get an extract or collect plants. They contain water-soluble biomolecules which are biodegradable. So if you happen to use a plant extract and you throw it down the drain, it has no environmental impact. Absolutely zero. The other thing is you don't need sophisticated laboratory equipments to use a plant extract for the synthesis of nanoparticles. And most importantly, the majority of extracts both act as reductants and stabilizers. So how are you going to select the plants? That is a very important aspect. So initial screening of plants should be carried out to look for potential bioreductants. So you can search the literature to see which plants have what chemicals, and the phytochemical composition of those plants can help you decide whether this plant will be useful for nanoparticle synthesis or not. The other important aspect is these plants must be easily available. They should not be seasonal plants where you have to wait for one season to collect the samples. No, they should be easily available throughout the year. And preferences should be given to plants that are familiar and mostly edible. However, as far as I remember, the Indian government has desisted or asked people not to go for edible plants because it would cause an issue to the food chain. For potential bioapplications, the selected plants should have clinical relevance. If you are trying to make a nanoparticle that will be used for any bioapplications, then try to use plants that will have some biological or clinical relevance. So this way, you will see it in the further slides, that the biomolecules from the plants that will stick with the nanoparticles that you have made, and maybe the potency and efficacy of the nanomaterial will be more. And last but not the least, instead of looking for individual plants, you should go for a group of plants, the representative group of plants. If you go for one genus, then go for mostly the genus has similar phytomolecules, and you can use them for the synthesis of nanoparticles. Well, I would like to direct. This is where I would like to stop about my introduction, and I would like to direct you all to the review that I have published based on biogenic synthesis of metallic nanoparticles. And the cover was, we were invited to give a cover design. So this is the issue. You can search it out and download it. Moving ahead. So now I would try to like to talk to you about the work that I do. So I work in the area of material sciences and synthesize metal nanoparticles as well as graphene-based composites, mixed metal oxides. metal nanoparticles and graphene-based composites, we have been using wet synthesis as well as green synthesis. The green synthesis, since this talk is based on green synthesis, in my presentation, I will show you the nanoparticles I have synthesized using various plant extracts and how I have used them for biological applications, how I have used them for catalytic applications, and how I have used them for environmental remediations. So the plants that I have studied or selected for my studies were basically, since I live in Saudi Arabia, it's majorly a desert. So we have very less choice, unlike in India where you walk 1 kilometer and you will find many plants. So here we have selected mostly the plants that are present in the desert, such as Pulicaria glutinosa, Salvadora presea, and Origanum vulgare, and Phalanthus umbilica. Okay. So to begin with, I would like to tell you briefly about Pulicaria glutinosa. Pulicaria glutinosa is a large genus, just as I just mentioned to you, that you need to select a group where you are not bound or you will not run out of plant. So this is a large group, and it comprises of 100 species. And it has been used for traditional herbal medicines for various ailments such as inflammation and diarrhea. Now, the phytochemical evaluation of these plants have led to inform us that they contain large amount of phenolic groups such as flavonoids. So what did we do? We took the plant itself, the entire shrub, as you can see. We dried them and we powdered it. Now, once we powdered it, we dissolved it in water. We dissolved it in water, and to this we added the silver salt. And within 2 hours of reaction time and 90 degrees, at 90 degrees centigrade temperature, we were able to obtain amazing silver nanoparticles. This is the place where this is the characterization that we have carried out. So basically, you will see that silver nanoparticles are visible in the range of 380 to 450 nanometers. However, it has been found that when you do UV analysis, if you get a broad peak at higher wavelength, that means you are slightly having a larger particle. And if you get a narrow peak at a shorter wavelength, that means you are getting you are getting a smaller particle. However, in our case, if you see, we have done the reaction in at two temperatures. One is 90 degrees and the other one is at room temperature. And you see that the 90 degrees, the UV absorbance has slightly shifted to the right. And this can indicate that the particles are slightly larger than the ones that we obtained at room temperature. However, if you look at the next graph, you can notice that when the reaction was carried out at room temperature, it took 36 hours for us to get the desired products. While when we did the same reaction at 90 degrees centigrade, the reaction was complete within 2 hours. And below, I would like to I would like you to see how the color is changing with time. And in 2 hours, we get a solution that is dark enough, and the formation of the nanoparticles has been confirmed by UV. The other study that we did was we varied the amount of plant extract. We varied the amount of plant extract, and if you see the A section of this graph, we have used about 5 different volumes of plant extract. And all these experiments we carried out at 90 degrees centigrade. And it was observed that the concentration of plant extract exerted significant effect on size of the nanoparticles obtained. And how could we say that? Because there is a shift in the lambda max of the UV spectrum that we obtained. As I just told you, broad peaks at higher wavelength indicate that they are larger particles, while narrow peak at lower wavelengths are indicative of smaller particles. So if you can see that in case of 1 to 5 ml of plant extract, the nanoparticles are slightly less, if you notice, in size. However, when you increase the concentration further, then the lambda max is shifting from 422 nanometers to 459 nanometers, which indicates that the particle size is slightly increasing. In the B section of the same image, you can see that a comparative study was carried out to investigate the effect of silver nitrate concentration. So if you can see that we have used 1 millimolar, 2.5 millimolar, and 5 millimolar of silver nitrate solution. And based on the study that we found, that when the plant extract is kept, and how did we do it? We kept the plant extract at 7.5 ml, and we used the various nanoparticles. So if we found that when silver nitrate, 1 millimole of silver nitrate was used, we got a lambda max of 447 nanometers, while when we used 5 millimole, it was 455, indicating that as we are increasing the silver nitrate concentration, the particle size was increasing. Moving ahead, we subjected the obtained nanoparticles that were isolated by centrifugation to various other techniques such as XRD and TEM analysis. So the XRD, it revealed that the nanoparticles, the silver nanoparticles that we were working on, were crystalline in nature. And the XRD pattern that we obtained revealed that the silver nanoparticles that we got was face-centered cubic structure. The 5 distinctive diffraction patterns that we found were very much in accordance to the reported silver nanoparticles. However, the intense reflection at 111, if you can see, at 2 theta, that is around 37.5 degrees, indicates that the growth of the crystal direction is in this index. Moreover, when we subjected this XRD pattern to a Debye Shearer law to calculate the crystallized size, we found that the average crystallite size was about 42 nanometers. The other thing that that you should observe is in the TEM images, if you can see, the scale is around 100 nanometers in A and B, and you can see that the particles appear to be very, very minute. The average particle size that we got was in the range of 40 to 60 nanometers, as per the TEM image that we got, and we found that there is slight amount of agglomeration that is visible. However, those images are not included here, but once we took the plant extract, when we took the images of the nanoparticles prepared by slightly higher amount of plant extract, the agglomeration was avoided. Furthermore, the interesting and most important aspect of a plant extract is, as I mentioned during my introduction, we would like to see some reagent that can reduce the metal salt as well as stabilize the metal salt. Now, in order that the metal salt is stabilized by the reducing agent itself, the reducing agent should stick on to the nanoparticles, the surface of the nanoparticles. So in order to find out whether the the nanoparticle is available on the surface of the the plant extract is available on the surface of the nanoparticle, we subjected the plant extract as well as the nanoparticles prepared to FTIR analysis. And in order to see to it that we don't have any residual plant extract, these nanoparticles were washed several times and centrifuged at high speed so that any traces of unbound plant extract on the surface of the nanoparticle should be eliminated from the system. We should be able to remove it completely, and we should get only the signals from the plant extract that is bound on the surface of the nanoparticles. So efforts were put in just to see to it that we don't have an error. And to our amazement, we saw that the FTIR spectrum obtained for the nanoparticles which is A, is very much similar to the FTIR spectrum obtained from the plant extract, indicating that these phytomolecules not only reduced the silver nitrate salt, but they also stabilized it to regulate the size and shape. So this was a very interesting finding that we found. And as I told you that Pulicaria glutinosa, the plant extract that we used for this synthesis, has been used as herbal medicine, traditional medicine in Saudi Arabia. So we subjected the prepared nanoparticles for various antibacterial or antimicrobial studies against various strains. So for this, we selected 2 gram-negative and 2 gram-positive strains. This graph that you are seeing is the optical density at 600 nanometers versus time. So in this experiment, what they have done is they have first subjected these bacterial species to to this plant extract, and they have calculated the optical density. If the optical density falls, that means there is the death of bacteria and the plant extract is working. So these 4 images that you see are the biological the plant extract, effect of plant extract on the various bacterial strains. And if you can see that there is no significant drop in the optical density, even when we use it until 500 microliters, 500 micrograms. So moving ahead, what we did, we subjected the nanoparticles that we obtained for the same bacterial strains that we tested for the plant extract. And we have found that the plant extract was not exhibiting any bacterial activity. However, the silver nanoparticles with these plant extracts was showing amazing antibacterial activity against E. coli and Pseudomonas aeruginosa. However, with regard to the gram positive, the bacterial activity was not very successful. So we can say that the silver nanoparticles that we prepared are selective for gram-negative bacteria. This work we published in International Journal of Nanomedicine. One was only the synthesis, and the second one was an in-depth antibacterial analysis of this. Moving ahead, we used the other plant that we used, Salvadora presica. With regard to Salvadora presica, this is also very much locally available in Saudi Arabia. And what we did is we used the root extract of this plant. And these roots were collected, and the extract was removed. And as you can see in this pictorial representation, that the root extract was mixed with silver salt, and we obtained silver nanoparticles in 2 hours. These silver nanoparticles were subjected to antimicrobial analysis. However, in this study, what we did was we compared the green synthesized silver nanoparticles with the chemically synthesized silver nanoparticles. Just to keep it brief, as we have already seen, that the silver nanoparticles have a signal between lambda max 380 to 450. And what we have done is we have used varying amount of root extract for the synthesis of the silver nanoparticles. And we have done this reaction at 90 degrees centigrade, and we found that the reduction of silver nanoparticle is complete within 2 hours. And the root extract at lower volumes, you get between 0.5 to 3 ml. You get amazing nanoparticles. However, when you increase the root extract volume to up to 5 ml, then the nanoparticle will cease. There is no further change. So in order, so for this study, we have used a root extract of 3 ml as standard. And as mentioned in my previous study, the role of plant extract as a reducing agent as well as stabilizing agent was again tested by FTIR. And if you can see, the red FTIR spectrum is the one from the plant extract, whereas the green is from the silver nanoparticles prepared from the plant extract. However, the blue, if you can see, is from the chemically synthesized silver nanoparticles. So if you can observe that the green synthesized nanoparticles contain the phytomolecules of the plant on their surface, which is evident from the FTIR, while the chemically synthesized has given no signal and it is just a straight line. Moving ahead, when we did XRD of this particular compound, we found all the peaks relevant to the silver nanoparticles. However, we also found additional peaks. These additional peaks indeed had baffled us as to what it is. And in the later slides, I will show you what it turned out to be. So the TEM of this nanoparticles revealed that the particle size is between 10 to 20 nanometers. And the nanoparticles are well distributed. However, you will see some chunks, very minute chunks, where agglomeration is still available. The EDAX also gave us the confirmation about the presence of silver as a major element. However, there were other elements that were also found in the EDAX. Stability of nanoparticles is a very, very important concept, because once the nanoparticle starts agglomerating, then they get converted to bulk and they are useless. So we did one dispersion of the synthesized green synthesized silver nanoparticles and chemically synthesized nanoparticles. Okay, so we took 5 milligram of each and dispersed it in 10 ml of deionized water via sonication. And we found that even after 2 days, the plant extract synthesized silver nanoparticles, the dispersion was intact, while you can see after 2 days, the chemically synthesized silver had settled at the bottom. So this shows that the plant extract is doing an amazing job of stabilizing the nanoparticles, which is a very, very much desired property for any nanoparticle. Moving further, we used the same nanoparticles for various against various microbial cell lines. Again, we used gram positive and gram negative. And it was evident that with the increasing volume of root extract for the synthesis of nanoparticles, we were getting a better antimicrobial activity against the tested strains. If you can see that when it was 0.1 ml, it was merely active against both the two cells actually. And as you keep increasing the root extract concentration in the reaction, the antimicrobial activity has very much enhanced. And for the comparison with chemically synthesized silver nanoparticle has also been displayed, that it has been shown that the silver nanoparticles prepared from the plant extract has comparable, or in some cases as Staphylococcus aureus. In case of Staphylococcus aureus, it is much better than the chemically synthesized silver nano. So this proves that the silver nanoparticle that we obtained has better antimicrobial activity. The plant extract is doing both the jobs of reducing the salt, as well as it is stabilizing the nanoparticles. So this work we published in Molecules, and anybody can go and refer it. Moving ahead, we slightly changed our focus from pure nanomaterials to nanocomposites. And since graphene is a very exciting material, and recently after the exfoliation of graphene, or I can say chemical exfoliation of graphene, where people were able to separate the sheets of graphene, the study has become even more exciting. So this separate sheets of graphene, it is usually termed as highly reduced graphene oxide. And how is it done? It is done in such a way that first you take graphene, you take graphite, and you chemically exfoliate it. You chemically exfoliate it using KMnO4 and hydrogen peroxide. And as you can see in this structure, the sheets have separated. And this separation of sheets gives us enhanced surface area to deposit any metal of our choice. However, this exfoliation gives a graphene oxide, but there is one more step that is required. That is, first you will remove the oxygen containing groups from the surface of the graphene chemically, and then you will add these metal nanoparticles. However, in our study, what we did, we prepared graphene oxide chemically, and we in situ tried to reduce graphene oxide as well as the silver, as well as the metal salt in some cases, and in some cases only graphene oxide. So as of now, I will just talk about how we have reduced graphene oxide, and in the later we will see how we have added nanoparticles. So to begin with, we have done we have done the synthesis of graphene oxide, and we evaluated it using UV spectrum. And as UV spectroscopy is a very sensitive spectroscopy for us to understand as to what is going on, Graphene oxide usually gives absorption bands at 230 and 301. Okay, so the red line is graphene oxide. It gives at 230 and 301. However, the desired product that we want is highly reduced graphene, which does not have these two peaks. So once we subjected the reaction mixture, which is evident in green, if you can see, P is the plant extract and HRG is highly reduced graphene. So P, HRG, if you see, these two peaks that are appearing at around 230 and 301, they disappear. They disappear, and you will see that there is a disappearance. However, in chemically reduced graphene, you will see a peak at 271. You will see a peak at 271. This is the black one, which will give you excuse me one second. So I was trying to explain the UV waves. So now this 271 is indicative of the total reduction of the graphene oxide, and you will get highly reduced graphene. However, in case of plant mediated reduction, you will see that there is a slight shift, okay, at 230 that has moved to 280, and this is because of the phytomolecules that are present on the plant extract, which they deposit on the graphene layer. So here we see that the disappearance of these two peaks at 230 and 301 and appearance of new peaks from the plant extract is indicative that the plant extract is reducing the graphene oxide as well as stabilizing it by depositing itself on the surface. Further, if you observe the XRD spectrum, the XRD of pristine graphene, or you can call it graphite, appears at 26.4 2 theta. However, during the course of oxidation, various oxygen functional groups enter between the spaces, okay, and leading to the shift, and you will see that there is a shift in there is a disappearance of this pristine graphene peak, and you will see there is a diffraction at 10.9, at 2 theta 10.9. However, this graphene oxide, when it is reduced, this 10.9 diffraction pattern that is observed in graphene oxide disappears, and then again you will come back to you will get a peak at 22.4, which is different than the 26.4 obtained for the pristine graphite. So this shift, this disappearance and appearance of new peaks in the XRD pattern indicate that the graphene oxide that was prepared from pristine graphite was successfully reduced to highly reduced graphene using the plant extract. And as I told you earlier, that the plant extract is not only reducing it as well as stabilizing it. It can be observed that the plant extract phytomolecules, signals coming from plant extract phytomolecules, are evident in the XRD spectrum obtained. Moreover, we also did the TGA analysis, thermogrammetric analysis of the graphene, highly reduced graphene that we obtained. And we found that the graphene or highly reduced graphene obtained from plant extract is slightly thermally less stable than the chemically reduced graphene. The reason is it loses, there is loss of weight that is observed. However, this loss of weight that is observed can be attributed to the phytomolecules present on the surface of this graphene, which decompose at elevated temperatures. Furthermore, we also carried out the Raman spectroscopy, because Raman spectroscopy is a very important tool for layered material. So for graphene, there are two main features that you observe, that is the G band and the D band, which are observed at 1575 per centimeter and 1350 per centimeter. However, when we use the plant extract to reduce these, when you use the plant extract to reduce this graphene oxide, these G band and D band, they slightly shift to 1582 per centimeter and 1343 per centimeter. And this shift can be due to the presence of phytomolecules, as well as when you make the graphene oxide, you destroy the sp2 structure of the graphene. However, when you reduce it, there is restoration of the sp2 structure, which is evident that because these two are very much similar, and the difference between these two values is 10 per 10. So it means that they are the graphene oxide, the highly reduced graphene that you obtain chemically, and the plant extract obtained graphene are almost similar. Another interesting study that we did was the XPS analysis. So the XPS analysis, we found that in the range between 284 to 290 electron volts, you get the carbon and carbon heteroatom signals, and mostly this heteroatom is oxygen. So if you observe, the top one is the graphene oxide, and the bottom one is the plant reduced graphene oxide. So the main peak that you see, the high intensity peak that you observe at around 284 nanometers, is the CC bond. This is appearing from the CC bond, whereas the 286 and 288 and 289, they are from the C and oxygen, CO and C double bond O and carboxylate kind of compounds. This intensity has reduced very much when we subject it to plant extract based reduction. And the minor that you see are maybe because of the flavonoids that are present on the surface of the graphene. The TEM images also reveal that the planar structure and the layered structure of graphene is intact, even after you reduce it using plant extract. Again, we studied the stabilization of graphene. And this time we used the plant extract obtained graphene, and we dispersed it in various solvents, and we compared it with chemically reduced graphene. And when we did that, we found that the plant extract obtained highly reduced graphene is very much stable in water. It is very much stable in DMSO and very much stable in DMF, while you see that the chemically reduced graphene is not stable in any of these solutions just after 2 weeks. So the stability of this graphene that we obtain is very much high and can be used for various other purposes. So this is where we published this paper. Moving ahead, as I told you in my previous work, that was dealing with reduction of graphene. Now here, what we did was we took graphene oxide as well as a metal salt, and we combined them to make graphene metal nanocomposite. So in this case, we use polycary agglutinose as the plant extract source, and graphene oxide was obtained by oxidation using Hummer's method, and we clubbed these three with the metal salt in situ, and we got amazing results. The if you can see, as I have showed you earlier also, that the UV-vis spectra has revealed that the plant extract is reducing the graphene oxide, which appears to be at around 240 nanometers, as well as there is an emergence of a peak between 380 and 420, which is indicative of the reduction of silver nanoparticles. So here we were successfully able to reduce the graphene oxide using the plant extract, as well as deposit silver nanoparticles on the surface of the graphene. Moving further, we did the XRD for the same, and we found that the highly reduced graphene, it gives us a signal at around 22.4 between 26, I'm sorry, 22.4, not 20, 26, I'm sorry. And silver also was present in the XRD spectrum that we obtained. So you can say that we were successful in depositing silver on the surface of the graphene, and the crystalline nature of the silver is intact. Moving ahead, we also did the Raman spectroscopy of this, and we found that the Raman spectroscopy of the plant extract obtained highly reduced graphene, and the intensity of the signals from the silver 1 and silver 2, which is varying amount of silver on the graphene sheet, you could see that the intensity has increased very much due to the presence of the silver on the graphene sheet. Moving further, this is the TEM image that we obtained, where you can see that the layered structure of graphene is intact, and we were able to obtain spherical nanoparticles, and to our astonishment, we found very little agglomeration on the sheets of graphene. So what did we do with these? We tested it against various cancer cell lines. So we used it against breast cancer, cervical cancer, liver cancer, lung cancer, and human prostate cancer. And we found that the IC50 value was best against lung cancer. So we selected lung cancer as our focus of study, and we carried out various other studies. In this, we were able to see that the cell cycle was stopped at G0 by G1 phase itself, indicating that the cells are undergoing apoptosis. But since I'm not a biologist, I cannot go deep into it. But this is what we were explained by our counterpart who did this. So I will not get into the details of the biological activity. However, we can say that these nanocomposites that we obtained were amazing against lung cancer cell line A549. And the mode of activity or the mechanism in which they were acting was apoptosis, that was cell death. So this work we published in International Journal of Molecular Sciences as well as in International Journal of Nanomedicine. Now, moving ahead, the previous slides were based on the biological applications of the nanoparticles or nanocomposites that we prepared. However, we also employed the same approach and used them for catalysis. And for this, we synthesized palladium nanoparticles. And palladium nanoparticles, for synthesis of palladium nanoparticles, again, we used Polycarya glutinosa. And we mixed it with palladium chloride salt. And we got amazing palladium nanoparticles, which was used for catalysis, and this was for Suzuki coupling. So just in brief, I will explain to you how we were able to conclude. So 450 nanometers is the range where you will see the signals that the UV max from palladium chloride. So in order to confirm the reduction of PD+2 to PD0, this peak has to disappear. And what we have observed is within 2 hours of time, we were able to see to it that this palladium chloride or palladium ion was totally reduced to palladium 0. And as I mentioned earlier, Polycarya has played a dual role in this regard also, where it has worked as a stabilizing agent as well as a reducing agent. And the palladium chloride nanoparticles were confirmed by XRD. This is the 10 microgram that we obtained, and you can see that these particles are in the range between 10 to 20 nanometers, and we don't see much of an agglomeration in this regard. However, we use this nanoparticles for Suzuki coupling, where we use bromobenzene and couple it with boronic acid, phenylboronic acid. To our astonishment, we got the Suzuki coupling product within 4 minutes. At 100 degrees centigrade, we got 100% conversion of the reactants to the product. This work was published in Transaction, and we were again invited to give a cover image for this work, and This is what we provided them with. Moving ahead, we use Salvadora Aprecia for the synthesis of, again, the silver palladium nanoparticles to see how it works with palladium. And we were very happy that we got amazing results as palladium by UV vis, and the crystalline nature was confirmed by XRD. And you will see in this spectrum, in the XRD spectrum, you will see additional diffraction pattern along with the palladium diffraction pattern, and this is because of the inorganic moieties present in the plant extract, which reveal themselves in the XRD spectrum. The TEM microanalysis revealed that the particle size is between 10 to 20 nanometers in this case, and they are very fine, minute particles around. But at around 4 to 5, you have the major chunk of nanoparticles. The EDAX has confirmed the presence of palladium salts, and we use this for. In the previous study, we just used bromobenzene as the precursor. But however, in this case, we used bromo, iodo, and chlorobenzene. And we have seen that iodobenzene reacts the fastest, and we get a product within 5 minutes of reaction time, whereas bromobenzene, we get 100% conversion in 8 minutes, while chlorobenzene gives us about 80% of the product after 24 minutes. Moreover, we use this palladium nanoparticles several times, and we found that there is a substantial reduction in chemical activity, catalytic activity, which can be due to the deposition, the loss of the phytomolecules that are present, that are on the surface, as well as loss of reactant or catalyst during workup. So we were not able to confirm as to what was the reason. So this was published in the Journal of Saudi Chemical Society. This is another plant, Origanum vulgare, we used for the synthesis of palladium nanoparticles again. And in this case also, we used it for the conversion of bromobenzene to reaction of bromobenzene and phenyl boronic acid to get a Suzuki coupled product. As you can see, that the UV is indicative of the formation of palladium nanoparticles, whereas the XRD is revealing the crystalline nature of the palladium nanoparticles, along with another diffraction patterns. However, this could be due to the phytomolecules or some crystalline substance present in the phytomolecules. The particle size is amazing here. We got an average particle size of 2.2 nanometers using this plant extract. And the stabilizing effect of the plant extract was confirmed by the FTIR spectrum, which was showing that the presence of plant extract on the surface of the nanoparticle, as well as the UV confirmed the reduction. We used this against various. We used various amount of plant extract in this study to find out which nanoparticle obtained from plant extract will give us the best activity in the least time. And it was found that when we use 1 milligram of plant extract for the synthesis of palladium nanoparticles, you will get 100% conversion within 40 minutes. Unlike the Pulicaria and Salvador Precia, where we got the product in 5 and 4 minutes. However, when you increase the plant extract, you can observe that the reaction is not going to complete conversion, which can be due to the deposition of these phytomolecules on the active sites. So when you increase the amount of phytomolecules, then the active sites are also blocked and it is not available for the reaction, even after an extended period of time. Moreover, we used this plant extract for several times, but it was found that after the second use, this palladium nanoparticles could not be reused because there's a steep drop in catalytic performance. This work we published in Molecules. The last part of my presentation is Phyllanthus umbilica leaf extract, and in this method we did not do wet synthesis, but we did combustion synthesis for the preparation of copper oxide nanoparticles. And we found that at 400 degrees centigrade, when this solution and the plant extract, the mixture of plant extract and the solution is burnt in an oven for 5 minutes, we get amazing copper oxide nanoparticles. So the copper oxide nanoparticles, you can see they have a lambda max, which is very much different than the plant extract. And as observed, that the crystalline nature of the copper oxide nanoparticles was confirmed by XRD. However, there were another set of diffraction patterns that were obtained, which could be due to the presence of phytomolecules or some inorganic impurities in the plant extract. The XPS analysis revealed the presence of copper and oxygen in the desired oxidation state. However, the zeta potential analysis also revealed the dispersion of the nanoparticles, and it reveals the dispersion of nanoparticles, and the particle size that we obtained from this study was about 92.3 nanometers, the average particle size that we obtained, which is much higher than anticipated. However, these nanoparticles were used for the removal of arsenic from wastewater. Okay. So there were 3 studies that we did. We studied the effect of nanoparticle dosage, the effect of variation in pH, and the effect of time. So in case of nanoparticle dosage, we varied the nanoparticle dosage from 1 milligram per liter to 10 milligram per liter. And we found that as you increase the concentration of copper oxide nanoparticles adsorbent in the reaction mixture, okay, you will see that there is an increase in absorbance. There's an increase in absorbance, and the maximum absorbance of arsenic was obtained was about 71% at 15 milligram per liter of copper oxide nanoparticles. However, for this study, we have varied the pH as well, and we varied the pH between 2 to 12 nanometers, nanometers, and we found that at 12 nanometer at 12 pH, these copper oxide nanoparticles have the best removal or absorption capacity at highest pH. However, when you are decreasing the pH, the absorption potential also is decreasing. Moreover, with the effect of time was also studied, and the nanomaterials were subjected to a prolonged time, were exposed to this arsenic solution for a prolonged time, and it was obtained that when you after 400 minutes of exposure time, there is no change in absorption. Yani, the absorption max is obtained or achieved in 400 minutes, and you will not have any further absorption based from the substance, from the solution. The kinetics of the reaction was also studied, and we found that the absorption follows a second order kinetics, because the data fits perfectly well for second order rather than the first order, as can be observed here. This study we published in Sustainability, and you can refer it for your work. However, we have also there are several studies that are being carried out, and since Dr. Shubha is one of my collaborators, we have recently published this study with her, and this is a collaborative work, and I'm very thankful to Dr. Shubha to take me on board and involve me in this study. So in conclusion, I can say that we have used various plant extracts, and we were able to obtain highly crystalline silver and palladium and silver copper oxide nanoparticles. These the reactions were carried out under aqueous conditions without any harmful solvents. The size of the nanoparticles could be controlled using by varying the concentration of the plant extracts. The plant extract is doing the dual role of acting as a reducing agent as well as a stabilizing agent, and we were able to the nanoparticles that we obtained were used or evaluated for their biological and catalytic properties, and they have shown amazing catalytic properties. Moreover, the plant extract, when compared with the chemically reduced or chemically prepared nanocomposites or nanomaterials, the plant extract was found to have an amazing effect on the dispersibility of the nanocomposites that were obtained in terms of, you can say, graphene oxide as well as the other nanoparticles. More studies will be required, because these plant extracts are very cost effective and reliable, and they save a lot of energy. However, a little bit of attention is required as to how the mechanism of the reaction goes on. The reason is the plant extract is a mixture, or you can say it is a cocktail of different compounds. So most of the studies that we have done, and there was a study that we were doing where we tried to isolate the active component from a plant extract and synthesize nanoparticles using it. To our astonishment, we did not get the desired nanoparticles. The reason is these cocktails, they are working in synergy with other phytomolecules that reduce the metal salt or graphene oxide, as we have seen in our case. So more studies are required as to which active component, or you can say which mixture of phytomolecules will give you the best results, so that the other components can be used for various other studies. So these are my collaborators, as has been mentioned. Dr. Ahmed Kamal is my PhD supervisor. He's scientific advisor to the Chief Minister of Telangana now, and Professor Wolfgang is a professor from Johannes Gutenberg University. We have almost about 35 publications with him, and he's an amazing chemist. So Professor Luz Mirzan, we have Shamstar Rez, we have Hari Babu, we have Dr. Shubha from your institute, Dr. Muhammad Bilal, and Vijay Kotra from Malaysia. So thank you for your time. This is my group of people whom I work with. On my left side is my student who's going to finish his thesis, and the right side are my colleagues. I'm also an editor for this journal, Journal of Saudi Chemical Society. I invite you all to submit your work there. The impact factor is about 3.9, and you will find a fair review. So at last, I would like to thank all my colleagues, and thank you all for your time and for the patience.
Thank you so much, sir, for excellent session and guidance. And we have received a couple of questions in the chat box, sir.
Yes.
Would you like to answer, sir?
1 second. Let me see.
I'll read it, sir. I'll read it, sir. No problem.
Yeah. Can we prepare this? Okay, I'm reading highly informative. There are two questions from Kailash Chandan, right? Do we have to use freshly prepared plant extract or dried leaves extract can also be used to synthesize nanoparticles? See, actually, this is a very good point that he has raised. We have seen that when we dried certain plants and we use them, and when we use them fresh, the extracts from fresh, we found that there is a slight difference in the nanoparticles. So what is happening is, when you dry them, there are certain essential oils that evaporate. So if at all this is a study. I cannot for sure say this plant should be used as fresh and this plant can be used as dry. No, but you have to try it out. I'm sure you will get different results when you use fresh as well as dried. However, most of the studies are using dried leaves because wet or fresh usually have a lot of moisture with them. So this moisture will interfere with the availability of the phytomolecules. So I would suggest you go for dried itself. However, if you want to particularly see which component is, or you have found some essential oil or some volatile compound in fresh, and you want to test it out, you can go for freshly prepared. The next question is, can nanoparticles be synthesized using plant extract prepared by organic solvents? See, actually, this is a point that you should remember, that metal salts are soluble in water. They are not soluble in organic solvents. So the plant extract, if you are obtaining it from any organic solvent, that means it will not dissolve in water. So when it is not going to dissolve in water, there is a possibility that there is no interaction between your metal salt and the phytomolecules of the plant extract. So okay, now there was one study we did where we dissolved the metal salt in methanol, and we subjected to an extract from organic solvent. But as per my finding, I did not get the desired nanoparticles. So I would suggest aqueous extract will be the best. Okay, then the second, this is Swastika Das. Can we prepare doped nanoparticles by? Yes, yes, of course. Of course, Ms. Swastika, we can go for any kind of doping, and as I just showed you with Dr. Shubha, we have prepared a heterostructure comprising of 3 metals. So we can go for it. You can go for it and try it out. And if you need any help, any guidance, I'm available. My contact details are there with your team. You can surely contact me. There is one more question from Pratibha, Dr. Pratibha BS. Okay, Dr. Pratibha, how much plant extract was added in the combustion method? Actually, we did not take it in ratio. In the combustion method, we have used 10 gram of plant extract for 1 mole of metal salt. And the next question is, how do you optimize the plant extract addition? Optimization is, optimization is a study. You as I have presented in my slides, we have tried various concentrations of plant extracts, and we reached one conclusion based on the UV vis. And once we were able to confirm that, then that sample was further studied for TEM and other analysis, so that we were able to get the desired product. Okay, so this is how you will optimize it. It is a study. You have, there is you cannot say for sure that this amount will help you in your nanoparticles. I think I have answered all questions. If there is anything else,
still more questions are there, sir.
Some more questions are there, sir.
Where is it, Dr. Shiva? Can you tell me?
Dr. Prasanna.
Dr. Prasanna from Davanagere.
Okay, one second. Let me. Can you read the question? I'm not able to see it. Dr. Prasanna.
Sir. Yes, sir. Just a moment. And you have answered one in that, sir. How to optimize the plant extract addition?
Okay.
It is asked by Dr. Prasanna from Davanagere.
Okay.
And how much of plant extract was added in combustion method?
Yeah, I have ordered that. That is Dr. Pratibha BS. I have answered that.
As well as asked by Dr. Prasanna, sir, from Davanagere.
Okay. Yeah.
And many of them have replied, sent message in chat box. Excellent session and informative, fruitful session.
I really hope it helps you, and I am delighted. I am frankly speaking, I am delighted.
Giving us best knowledge, like keep on, we are receiving the messages. Thank you so much, sir.
Thank you so very much for inviting me, and I thank the entire management of this institute, Don Bosco Institute, for this amazing program, and I am available any other time you invite me to.
Thank you, sir.
Thank you
sincerely,
so much.
Yes, sir. Proceed, please, sir.
Yeah. Thank you so very much. So I think I can leave now, right?
Sir, yes, one second, sir. Please, just a moment, sir.
Yes.
We sincerely thank our chief guest, Dr. Syed Farooq Ali, sir, for kindly accepting our invitation and gracing the inaugural function. Now, as a token of gratitude, we are interested to share appreciation certificate. Please accept it, sir.
Thank you so very much. Thank you so very much.
Be inspired and enlightened by your keynote speech, sir. Thank you so much, sir.
Thank you so very much. Thank you.
Sir, we are blessed to have you, sir.
Thank you so very much.
Thank you, sir.
Thank you so much. Okay, then. Bye. Yes, sir.
Thank you very much, sir.
You are welcome, sir. The pleasure was mine. Thank you so much for
inviting, sir.
Yeah.
Thank you so much.
Okay, sir. Bye-bye, sir. I'll hang up now. Okay, then?
Yes, sir. Thank you, sir. Thank you, sir.
Okay, bye.
Feedback link is shared in the chat box.
Yes. participants, kindly give your valuable feedback. Next session, you please join the next session afternoon by 1:50 itself. 1:50. Thank you so much for the patience listening. Okay, so with your kind permission, we will end the meeting now. Thank you so much. Thanks for participation.